it turns out right here where this little star is, that's the center of rotation of all these objects. I'll show you another video like this in a minute. That's the center of rotation of all these objects, and the objects have elliptical trajectories, which are indicative of the fact that they're in orbit around a central mass. The properties of the rotation rates of the stars allow us to calculate the mass, and it's 4 million suns. So these are objects that are all orbiting the black hole at the center of our galaxy. Here's a drawing, a little more detailed.
Don't you need to know the mass of the stars to do that?
No. You just need to know their orbit parameters. When you do the arithmetic, the mass of like Earth's mass disappears from the equation. It's its orbital radius that matters, and we get everything we need from that. This is a picture of the vicinity of what we just looked at. This is visible wavelength. Oh, okay, here's the other video. This is the lead professor, Andrea Ghez. Now, here she's backed out. She's not looking as deep as she can. She's backed out and she's looking at stars in a larger area. Actually, at the end of the video, they tell you the spatial scale. But this is real. I mean, this is not an animation. This is the motion of stars near the interior of our galaxy. And they're all in orbit around the black hole. A couple of eccentric ones that are out. I mean, most of them are orbiting in that plane.
Why are they expanding as if it were dark matter, dark energy?
Oh, she's just zooming back. That's an effect.
Oh, because you would think they're being drawn into the
Oh, yeah,
gravitational.
but what you're seeing,
Dark matter.
you mean the fact that things were changing scale?
Yeah.
That's just to make it visually interesting.
Oh.
This is,
But am I correct in thinking that it should be the opposite in terms of the dark matter pulling in? toward
now
the black hole?
these stars are in stable orbits. Their orbits are not changing. So let's make sure that there's nothing here is related to the expansion of the universe. We're looking at the orbits of stars deep in our galaxy.
Do all galaxies have that black hole concept?
Yeah,
That's why when you look at the Milky Way, you see the elliptical sort
yeah.
of things.
It's not for certain, but the general consensus is that every galaxy has a supermassive black hole
Yeah, so
in its center.
that makes sense.
And the question is, what is the genesis of the black holes? Were they born early in the history of the universe and collected matter around them, and we call that matter galaxies? Or was there just a random collection of stars in a neighborhood and they said, you're the biggest one, why don't you be the black hole? And a bunch of matter fell in, and that object became massive enough to become a black hole and consumed the neighborhood. This is, I'll get to you in a second, let me make this point. This is another issue about a research topic of current interest is when black holes form, they have this accretion disk that's extremely hot and lots of energetics going on there. Some galaxies appear to have blown away the interior star. So you have a big galaxy, and there's a black hole, and there's nothing near the black hole. And we can tell that because the black hole is not eating anything. When the black hole is consuming things, there's a kind of a flare-up of energy as the accretion disk heats up. But there are galaxies that are essentially like a ring. There's a black hole in the middle, and the interior section is empty. It looks like an automobile tire. And it's possible that happened because when the black hole formed, the energetics of the formation and the heat of the accretion disk were so high that it blew away all the nearby stars, and there's nothing else for that black hole to consume. So it's just there by itself and will never encounter another, it will never have another meal. Yes, sir?
In the animation, which wasn't an animation, picture of the stars rotating the black hole, it appeared that almost all of them were in almost a plane.
Yeah.
And the galaxy itself is in a plane.
Right.
Why wouldn't it be three-dimensional? Why wouldn't it be sphere?
Yeah, that's a good question. We don't know. It's possible that the evolution goes like this, that the primitive group of stars that form the galaxy are just in a kind of a cloud. But as more material arrived, some of the cloud gets thrown away. That is, the energetics of some stars is that they are no longer stable in that environment and they leave that galaxy. And so the galaxy cleans itself up until it is a flat disk, which you can now see right now. You have a few oddballs like this guy,
Yeah.
but most of it is in a plane, and that's what as Ansel says, that's what our galaxy looks like. Of course, we have never taken a picture, but we know the motions of all the stars, and we can draw a picture. We are in a giant spiral galaxy that is flat to a large degree. Yes, sir?
Are all galaxies have a plane, like pinwheel plane, or some of them
No.
round?
No. You have these globular clusters, which looks like a hairball. And these are the oldest, these appear to be among the oldest galaxies. The reason I say that stars get ejected from galaxies is occasionally we find a star that's not in a galaxy.
There seems to be a physical thing going on of like our solar system is in a flat plane.
Right.
There the matter around Saturn
Right.
has gathered in a flat plane,
Mhm.
and then we have some galaxies that are pinwheels. I was wondering, does somebody ever theorize that the universe itself could be in a
Yes.
kind of a plate, kind of a
Right. So in prior meetings that you did not, you missed the first one,
Yes.
right? So we talked a little bit about this, the issue of the geometry of the universe versus the shape. And I made the point that you can have a flat geometry like a sheet of paper, but a flat geometry does not have to have a flat shape. Because I could roll up that piece of paper, it's still geometrically flat, but it has a different shape. And so the shape of the universe is an open question right now. There is some data in this video. It was a question of what is the scale? And somewhere, I'm not going to dwell on it, but if you look at the video closely, it tells you what the scale of light years is. Maybe it's written, let's watch this briefly again. But you can see kind of a tumultuous situation in the middle, but on a larger scale, things are flat. But somewhere in the video, I think they tell you what the scale is. I'm surprised, I don't know.
The tumultuous center, is that near the event horizon?
No, the event horizon is a property of the black hole.
And they're circling the black hole. So those closer, tighter orbits, like if we go back to that boat image
Oh,
going down in.
yeah, okay, I see where you're going. We're not seeing down to the scale of the horizon.
Okay.
I'll show you that we can. Oh, here's the information. Sorry. So where it says PC here, that you can treat that as light years. So the movie, sorry, the movie starts looking at the very interior of the galaxy, tiny fraction of light years and then moves out to a larger scale. Okay, so we've already talked about how light is bent by the distortion produced by gravitational objects, or energy. This can happen in this circumstance too. If we have an object here, and we're viewing it from over here, and there's some massive object in between, usually a galaxy, light can get bent both ways around this, and when I say both, this is a two-dimensional case. Light can get bent in all directions around that object, which may not be visible. It may be dark matter, for example. I'm going to show you some examples of how we look at the sky and we think we're looking at a single at multiple objects, when in fact it's different pathways for the same object. In this cartoon, we would detect this ray of light coming, and we'd say, well, it's coming from this object. And we would say this ray of light coming from this object, when in fact it's all coming from a single object. And here's an example. This is, there's a bright object out there that the Hubble telescope was looking at, and then there's some distribution of mass in between us and that object, and this is what you see. These, and we can tell these are the same thing, because they have the same redshift, which means their velocity away from us is the same, and they have the same spectroscopic content. So it's just 4 images of the same object.
I would have expected a circle.
That happens, that happens when we have a special word for that. So I'll show you that in a second. But see these little arcs here? These are distorted, particularly, look at this one. It probably has a companion over here. Maybe that little piece there and this are the same thing. Now Ansel's right. You can get a special case. Oh, see this one? That piece there and that there, those are from the same object. Here's one that's almost completely circular, but the alignment has to be perfect. It has to be a geometric straight line from our telescope through a spherical gravitational mass out to the object of interest. They all have to align, that's called syzygy.
So is in the middle one, is the light that's coming around being distorted by the middle light there?
Possibly. A lot of times there are other objects in the picture. Now whether this little ball of maybe globular cluster, one of those spherical galaxies, whether that caused this or some other object along the path, I don't know. So you see these kinds of things. Here's one. And this is a cartoon to show that we see this ring, if everything is lined up exactly right, we see this ring because this object got distorted by something close to spherical, like this galaxy, and we're here observing. And this is the word syzygy. So now I have some other animations. Oh yeah, and now let's take a look at an extreme case to try to help you see the distortions that can occur. Suppose we have this kind of weird cartoonish worldview. What we have is this cylinder and a ball and an ocean and other kinds of objects, and now we're going to position a black hole between us and this scene. And we see this. Because all the light rays get bent depending on the path they are taking to our telescope. And a lot of light from this scene produces light that we don't get to see because the distortion produced by the intervening mass makes that light go somewhere that doesn't encounter our camera. So some of this, that's why I said in the motion pictures, the Australian videos I showed, where you see all the light gets forced in front of you, the light rays all get, the trajectory they follow gets changed because there's a mass in the way. So those of you who saw the movie Interstellar, they made a big deal about this supermassive black hole. they called Gargantua. And this has something interesting about it. So let's imagine there's a black hole in the neighborhood, and there are black holes in our galaxy, other than the supermassive one. Let's talk about what it means to see something. So you can see me because light comes to me, reflects off of me, and comes to your eye. Imagine you were out in space 65 million years ago, looking at Earth. You would have seen forests and dinosaurs and whatnot. That means there's light coming from the Earth. The sun illuminates Earth. The light reflects from the dinosaurs. And so that light is coming upward from the Earth to you as an observer. And some of that light may have gone out and encountered the black hole in the galaxy as it existed then. And what this drawing depicts is that light that encounters a galaxy, encounters a black hole, depending on how close it comes, that light may go into orbit around the black hole. And some of it stays in orbit permanently. And some of it makes multiple orbits around the black hole and then goes back from whence it came. So here we are on Earth, and this is just a thought experiment. If we look up at the night sky, some of the light we see coming to us actually had spent millions of years traveling to a black hole, orbiting the black hole, and then made its way back toward us. And if we could collect enough of that light, we could take a picture of the dinosaurs. Now, in real life, could you do that? No. But it's an excuse for putting a dinosaur picture. But this is a field of research where light gets trapped going around, orbiting around black holes. Here's what happens as we speed up. This is very similar to the Australian video I showed you where things got distorted. So, speed over here. Notice everything looks like it's going away from you, when in fact what's happening is, as your speed goes up, notice up in the upper right, your speed is increasing. As your speed goes up, the things beside you start moving toward your direction of motion. That's why it looks, we're seeing more stars, which makes it look like we're backing up, when in fact, more stars are visible because we're going faster. And the stars that are there are getting brighter. So if we are, and now we're traveling about half the speed of light. Notice what's happening here. Lots of stuff that we did not see in the first frame of this video is now visible to us. And everything's getting brighter in front of us. And I know we have one pilot in the room who would not want to fly into an area where all you see is a bright light. You have no idea what solid objects are there that might collide with you. But this is a physics-based simulation. I want to make sure you understand it. Hollywood can produce simulations of what happens when light encounters massive objects. The right way to do it is use physics to do it, not just to make it visually attractive, but to actually use Einstein's theory to create. This is a result of Einstein's theory tracking the rays of light as your speed increases and increases. And right now, right here, we're at 282,000 kilometers per second. When we get to 300, we're at the speed of light. This was done using a picture of the galaxy and then distorting it using physics. This is the belt of our galaxy. But notice now we're in a situation where we're almost at the speed of light and everything is in front of us. And this ends when we get to the speed of light. we'll just let this play to the end for the effect of it. So if you're zooming through the galaxy at near the speed of light, steering around objects is a bit of a challenge. Yeah, so we're almost done. Yeah. It's this video again. Now, let's talk about the distortions that occur. Here's a depiction of, or actual image of a part of the galaxy, our galaxy, with, and now synthetically put a black hole here. And let's see. As the galaxy rotates, this is the kind of thing you see. Notice some of the objects, let's see, right here, this guy, or you can pick one with your eye, you might find one, they're going this way, and then they stop and they go back the other way. And this one, see that one, is this one. So things are going back and forth. This object is this object. So we're seeing multiple copies of each object. And this is the horizon, and we don't see anything from here. So that takes a long time. We don't have to go through that. Here's a related one. Once again, using our galaxy stars as a starting point, and then artificially dropping a black hole into the scene and seeing what happens. So this is another way to depict what happens. So here's a synthetic set of rings, and we're going to place a black hole right in the middle. And this is what you get. The light from the distant part of the ring appears to us, but it comes over the top. By the way, these static images are from a book about the making of the movie Interstellar. So there is a book, it's called The Science of Interstellar, written by Kip Thorne, who is the intellectual father of the movie and is one of the great gravitational physicists of our time. He's also one of the parents of the gravitational wave sensors that are detecting gravitational waves all the time. So Kip Thorne I recommend one of his books is in my list of recommended reading. But this is what you see if you have a nice set of rings like this and you drop a black hole in the middle. And notice it's not symmetric. What I mean by symmetric, not the same on this side as this side. And that's because the black hole is rotating. Remember, it's an invisible tiny object. All the matter and energy that's fallen into the black hole is confined to a space smaller than an electron, but it can have the property of rotation. And the theory is that virtually every black hole is a rotating black hole. They have very interesting properties. So this is kind of what we're seeing here, that the distant part of this ring, which is here, that light made its way over the top to the camera. So we see this huge distortion. Oh, and let's go back. Well, we've seen something like this already. But that's available for you to look at if you want to. That link is there. Once again, here's this issue of the black hole. So here's the circumference, but the radius is getting, this circumference is what we would measure, but the radius is getting smaller. So the relationship of circumference and radius changes because in this interior region, space is distorted enormously. But there's something else on this drawing. See these arrows that say space drag? So what happens is